Hi there, I'm Eric and welcome to the most fun part of the course, Application Security. So this is where you're all going to become hackers. At least you should be becoming hackers at this point. So we'll be talking about a number of topics in different slide sets. So the first three are in this slide set and they form an introduction of sorts. We'll start off with an example of a buffer overflow, which is one of the simplest cases of application security exploits and memory exploits. Then we'll do an introduction, given what we've seen before, and we'll talk about local privilege escalation, which is important because you'll be doing this in the assignment. Afterwards, there's a bunch of more topics that we'll be discussing. We discuss simple attacks that do not require overwriting memory and so on, but can be done simply from the shell in the environment. Then we'll be discussing assembly language, which hopefully most of you already know, but for those who don't, there will be an introduction to assembly language because that's very much needed for the later topics. Then we'll be getting to the real fun, exploitation techniques. This is where you'll be breaking actual programs. And finally, we get to the defenses, because of course in the end, we don't want to break systems, we want to fix systems. And in this course, we learn how to fix systems or how to do them right by first learning how attackers work. So now let's start off with an example of a buffer overflow, which is, I would say, one of the simplest possible attacks where you actually get to target the memory in the target process. So one of the more interesting classes of attacks. This is also, by the way, a very widely used attack because it's an easy mistake to make. So here we have a program. Let's take a look. What is wrong with this program? So we start off in main. We call the hello function, supplying an argument to the function. This argument is used as the name parameter. Then we copy the name parameter in the local buffer called buff, and we print the local buffer. Do you have some idea what might be going wrong here? So I hope you've already spotted it, otherwise pause the playback now, because I'm going to reveal it. So the issue is that the buffer is only 16 bytes, but a potential attacker, any user, can specify as many bytes in the name as they want. So it's not necessarily the case that the name will actually fit in the buffer. So what happens if it doesn't fit? So this is where it gets interesting. So the core for a buffer overflow, we have limited space, but there's no limit on the data that we're putting there. Or of course, in other cases, the limit is too high. So it's possible to put something in there that really doesn't fit. Now, what happens if we actually try to compile and run this program? So we compile the program and we run it specifying as an argument the word class. Now the program prints hello class, which is expected. The string fits. It's only 5 characters and of course a null terminator, and this nicely fits within the 16 character limit of the buffer. So that works fine. Of course, if we make it somewhat longer, it still works. Right? Again, the program works fine. Nothing to be seen here. Now what if we try a much longer string? Well, this obviously doesn't fit in 16 characters. So what happens? The following happens. We get this weird output. Stack smashing detected. Terminated. Actually, the program thinks we're attacking it. So it turns out that modern compilers actually have some default defenses that protect against these kind of attacks. Well, as such, the program thinks we're attacking it and terminates. So to prevent us from abusing the program to gain control. Now let's see what happens without protection. So we use the -f no stack protector flag to indicate that this particular defense should be disabled. This defense wasn't used by default until relatively recently, so there are many programs out there that don't have this particular defense. Moreover, we'll find out later that it's actually possible to bypass this defense, even if it's on. But we're going to focus on the simple case first. So what happens now? We get a segmentation fault. The program crashed. Now this is something as hackers we really like to see. If the program crashes, it essentially always means that there is some kind of memory vulnerability in there. And probably by specifying the right inputs, we can get the program to do whatever we want. Also, the operating system is nicely helping us to debug it. Now this might come in handy. If you don't get the core dumped message, it may require specifying ulimit-c unlimited. This enables an unlimited size for core dumps. Many systems by default these days do not allow core dumps, so specifying a maximum size of 0. Another thing is that on the standard installation of Ubuntu, there's actually a system that handles the core dumps, which means you don't see them. So in this case, you also have to uninstall that program. However, in general, as a hacker, the important part is the segmentation fault. It means that the program crashed, and it means that something is going wrong, which for the attacker is a good thing. Now let me give you some background that will be relevant when you're starting to exploit bugs like this. So there are actually 3 types of memory in a regular C program. One is the stack. The stack stores all the local variables that are not static. Then there is the heap, which stores memory allocated explicitly by the programmer. So this is when you use calls like malloc and new. This is memory managed by the programmer that they have to explicitly allocate and explicitly release when they no longer need it. Finally, we have global memory. So global memory is essentially always there. It doesn't need to be allocated, it doesn't need to be deallocated. Now this is for global variables as well as for static variables. So now the question, we saw the program. Where does buff live? We will see that this is important for exploitation. Well, here we have the program again. So now again the question, where does buff live? If you need some time to think about it, please pause the recording now. So the answer is buff is on the stack. Buff is a local variable in the hello function, so it lives on the stack, which means that the compiler automatically allocates it when the function is called and deallocates it when the function returns. Now let's talk for a moment about stack frames. So ideally, you've already heard about stack frames in a computer architecture course, but just to be sure, we want to include a brief introduction here, because it's going to be critical in understanding how to exploit memory errors. So, a stack frame is a part of the stack that is reserved by a function for its own use. So whenever you call the function, it needs some space to store important state, such as local variables, and it gets a small part of the stack for that purpose. Now this part of the stack is then called a stack frame. So what information is stored there? So it's not just the local variables, but there's also some other stuff, such as the return address. Now this is very important. Whenever you call a function, after it returns, you go back to the original place it was called. So somehow the CPU must remember where it was called from. Now this is done on the stack. The return address is the address of the next instruction after the call to the function, and this instruction is returned to at the end of the function. Right? So the CPU stores this on the stack as part of the stack frame. Another is the frame pointer. This allows the function to keep track of where its stack frame is. Now this is useful, for example, to access local variables. Additionally, there may be other storage that the compiler needs. So for example, if some CPU registers, which we'll discuss later if you haven't had assembly yet, if some CPU registers are changed but must be preserved, they too will be stored on the stack as part of the stack frame. So the stack frame is managed by the compiler. The compiler emits instructions that create the stack frame, that store stuff there, and also to deallocate it when the function returns. So at call time, all these things that we discussed here are going to be pushed on the stack, whereas at return time, all of these will be popped from the stack, which means that the stack is in its original state again, from before the function was called. It's important to note that on x86 and on most CPU architectures, the stack actually grows downward, which is somewhat counterintuitive. So it means that when we put something on the stack, the top of the stack will go to a lower address. So any push decrements the stack pointer by the size of a machine word. So on a 64-bit system, it's decremented with 64 bits, that is 8 bytes. And every time we pop, then the CPU loads the data from the current stack pointer, the current top of the stack, and then increases the stack pointer, again by the size of a single machine word. So in this case with 8 bytes. Now let's look at a simple example for the vulnerable program that we saw. So we're executing currently in the main function, and we're about to call the hello function. On the stack right now, there's the return address of main and the frame pointer of main. So now, let's call hello. What happens to the stack? Well, we add a bunch of stuff, and this is to set up the stack frame for hello. So hello has a return address, and the return address points to the return instruction right after the call to hello. And then we also have the frame pointer, which points to the previous frame pointer as a point of reference for the function. Now, we start executing the next instruction, which allocates the buffer of 16 bytes. This too is added in the stack frame on the stack. Right? So allocating a variable comes down to pushing the variable on the stack. Although in this case it will not be initialized with any data. That happens in the next step. The string copy function will copy the value stored at name, so the string stored at name, and continues copying until it encounters a null byte. So the null byte in C is an indication that a string ends. So name is a pointer to a character, but in reality it can be an arbitrary number of characters followed by a null byte that indicates the end of the string. Well, string copy just copies the data and doesn't stop until it encounters the null byte. It is clueless how large its destination is. It simply gets a pointer to the first character of the buffer, as well as a pointer to the first character of the name, and it starts copying the name until it encounters the null byte. Now, let's see what happens. This is what happens. So, what happened is the function string copy was unable to fit the name into the buffer, but it had no clue. It didn't know where the buffer stopped. So it just kept on copying. And what it did is after the buffer, it continued into the remainder of the stack frame, overwriting all sorts of important stuff. So right now, both of our frame pointers are corrupted. The return address is also corrupted. The values stored on the stack are no longer correct. Well, what happens when we call printf then? Well, this is remarkably normal. It just executes and prints the correct value, as we also saw before. But now we reach the end of the function. So what happens? Do you have some idea? If you need to think about it, please pause the playback. Okay, so what happens if it's going to load the return address from the stack frame? And the return address is now overwritten with a bogus value. This means that the return address is no longer a valid code pointer. So we basically return to a random address. Now it's almost certain that at this particular random address there will be no valid code. In fact, it's very likely that there's nothing at all over there. So what happens is the program crashes. It tries to jump to an invalid pointer, but it cannot. So at this point, we managed to at least corrupt the stack of the program, although we haven't been able to do anything useful with it so far, but we will. So what do we learn from this example? Well, first of all, C and C++ are known as unsafe languages. They are low-level languages that assumes the programmer knows what they're doing. If the programmer makes a mistake or doesn't know what they're doing, anything could happen. So if we're going past the end of an array, it doesn't check. It just lets us. And we override whatever is next to it. So it is now the programmer's responsibility to make sure that they enforce array bounds. So, if you write outside the bounds of an array, then you overwrite whatever is next to the array. And if the variable lives on the stack, if the array lives on the stack, it's often the return address, which is right next to the local variables. And then the attacker gets to decide where execution continues, because they overwrote the return address. Right? In this case, we overwrote the return address with garbage, because we were not intentionally attacking the program. But if we overwrite the return address with a pointer to our own code, we can execute our own code. And this is a useful attack that is widely used.